So in studying kinetics, we learned that reaction rates generally increase with increasing reactant concentration. Did all this stuff with rate laws and stuff, and we increase the concentration of a reactant, the reaction goes forward faster, right? Well, in a reversible reaction, the reaction can proceed in the forward direction, and it can also proceed in the reverse direction. So as the reaction progresses, the reactant concentrations go down, and the rate of the forward reaction decreases. While that's happening, the concentration of the products increases, and the products are the reactants for the reverse reaction. So the reverse reaction rate increases, right, as more product is formed. At some point, the reaction rates become equal, and the rate of the forward reaction is equal to the rate of the reverse reaction. And that's the point at which we have what's called a dynamic equilibrium. So here's an illustration with some clocks representing time. We have illustrations of the molecules. Here we're looking again at H2 plus I2 makes 2 high. Very cheerful molecule, that one. So in this graph, we have the concentration of the reactants and products as a function of time. So when we start out, we have high concentrations of the reactants, and we have no product. So the forward reaction will go. And as the forward reaction proceeds, the concentrations of H2 and I2 go down, and that reaction starts to slow. Well, as these go down, the concentration of the product increases. The product is the reactant for the reverse reaction. And so this causes the rate of the reverse reaction to increase. So this will continue, these going down and these going up, until at some point the rates of those reactions are equal. And so even though we have forward and reverse reactions happening, we don't observe any change in the concentrations of the reactants or products. So this is a little bit like a busy airport in the middle of the day. Say there were 5,000 people in the airport at noon. And you take a survey, however you would do that, at 2 o'clock, and you see that there's still about 5,000 people in the airport. Is it all the same people? I hope not. Not if things are working how they should. Because airplanes are coming. This airplane comes and brings in 200 people. That airplane leaves and takes away 200 people, right? There's people coming in and going through cars and buses and things, right? So we have people entering the airport and leaving the airport. In the middle of the day, that's probably roughly equal, right? So we have roughly the same number of people all day long, but it's different people. It's dynamic. And so when we look at an equilibrium reaction like this, it's not static. There is constant forward reaction and reverse reaction occurring. Any questions about that?
So the dynamic equilibrium is when the reactant and the product are in the same amount of concentration?
No, actually. That's a great question, though. So the question was, is the dynamic equilibrium when the concentrations of the reactants and the products are equal? That happens with a very few, but not with most. So what's equal is the rate. The rate of the forward reaction, how fast it's going, is equal to the rate of the reverse reaction. So, dynamic equilibrium, the condition in which the rate of the forward reaction equals the rate of the reverse reaction. So, forward and reverse reactions still occurring, concentrations aren't changing, but as someone prophetically asked, they are not equal to one another. And that's kind of a natural thing to think. Well, if it's equal, then the concentrations are equal. No, they are not. The relative concentrations are going to depend on the value of that equilibrium constant, which is just something we have to measure and determine. So another analogy is, I guess you'd call this immigration. In an earlier edition of the book, instead of country A and B, which is kind of boring, this was Middle Earth, and this was Narnia. Isn't that more fun? They maybe got into copyright issues or something, who knows? So initially, there's a lot of people living in Middle Earth. There's very few people in Narnia. And so, people are curious, and so some of them are going to go over here, and they're going to like, oh, hey, there's a lot of space over here. It's kind of crowded where I was living. I think I'm going to move over here. It looks pretty nice over here. So we have people moving from Middle Earth to Narnia. If there's essentially nobody living here, we can't have people moving the other direction, right? There's not really anybody there to move back, right? But as more and more people move to Narnia, the population in Narnia increases, the population in Middle Earth decreases. And so now, because there are more people here and people are always dissatisfied with where they are, some of them are going to say, well, I'm going back over here because it's not so crowded anymore and this place is getting crowded, whatever the reason. So people will be moving in both directions now. So at any given time, the number of people living in Narnia is relatively constant, even though just like at the airport, it's not the same people all the time because people are moving in and people are moving out. Does that make sense? Any questions about that? If you change something, like, maybe there's like a plague of grasshoppers or something that comes to Narnia, well, that might cause the equilibrium to shift, right? Because now this is not as nice of a place, and so people are going to move to the other. So there are a lot of different factors that can affect the equilibrium. Okay, which statement does not generally apply to a chemical reaction in dynamic equilibrium? So let's just identify true or false as we go through these choices. The rates of the forward and reverse reactions are equal. True or false? True. So we're looking for one that's false. So that one's true. The concentrations of the reactants and products are constant. That one's true. It's not changing. The concentrations of the reactants and products are equal. That's false. So that's our choice. The concentrations are constant, they are not changing, but the reactants and products are still reacting and going back and forth. So just like the people in the airport, it's not the same molecules all the time. Those are changing, but the overall number of them is the same.